Hi, everybody. I'm Sidharth Gupta, and today I'm going to talk about a method for efficiently training deep neural networks to be robust to adversarial test samples. I think by now, some of us know that deep neural networks can be very sensitive to imperceptible perturbations in their test data. For example, on the top row, I have normal images from the CIFAR10 dataset, and the bottom row, I have the same images perturbed by a very small amount that may be almost imperceptible. The top row of images is correctly classified when I test it on a wide res net that I've trained on CIFAR10 images. The bottom row of images, however, are all incorrectly classified when tested with the same model. And the amazing thing is, for us humans, there's no reason why this should happen, and we would not struggle to classify both sets of images. And it has been known for some time that deep neural networks suffer from this problem, and there have been a variety of approaches to train models to be robust against such perturbations in test data. One popular method is regular adversarial training or adversarial training, and seeks to solve an optimization problem as shown here. Script L is the loss function of the neural network. F data is the deep neural network parameterized by parameters data. X is a training sample, and Y is the actual class of the training sample. So for each training sample, we try and replace it with an adversarial counterpart that maximizes the loss. And then we minimize the neural network's parameters on these adversarial training samples, rather than using the original training samples of the dataset. And to do this maximization, we use projected gradient descent, where basically we're doing gradient ascent on the loss function of the neural network. And after each iteration of gradient ascent, we project the sample to be within an epsilon ball around the true samples so that it still resembles the original sample. Now, the thing to note here is that in each epoch, we will most likely get a training sample that was seen in the previous epoch or previous mini batch. Now, because this projected gradient method depends on the parameters data of the neural network, every time a sample comes, we will have to regenerate an adversarial training sample of that original image. And because we require gradients of the loss function, we have to do forward and backward passes and multiple forward and backward passes of the neural network, depending on how many iterations of projected gradient descent we want to do. And the larger the network is, the more time consuming this can be. And then we have to do this for each image every time the image comes up. So in total, regular adversarial training can be extremely computationally expensive. And we actually measured this to check this. And this is CIFAR10 training times for two popular ResNet architectures. And we can see that the regular adversarial training time is much longer than the natural training time. So our goal of this work is to reduce the time of adversarial training, but still get performance that's comparable to regular adversarial training. So as we've established, the adversarial samples we use during training are dependent on the evolving model parameters. And initially, these model parameters randomly initialize, and they can be very different to the parameters of the final model. And as a consequence, most likely, the adversarial training samples used at the start of training are very different to the kind of adversarial samples that will be used at the end of training, and more importantly, very different to the kind of adversarial samples that will be used during testing to try and make the model misclassify. Yet, these initial adversarial samples, which are used for training for this initial starting phase, add significant computational overhead because we still have to generate these adversarial samples. And We can verify the usefulness of these initial adversarial samples in a simple experiment. We perform regular adversarial training on a wide ResNet for CFAR10, and I also saved the model parameters after every 5 epochs. Then I take the final model and I generate adversaries from previous epochs and test it on the final model. And the blue curve plots the accuracy when tested against adversaries from previous epochs. And we can see that almost for the first half, the adversarial accuracy is significantly higher to the adversarial accuracy that's attained at the end. And so this perhaps suggests that adversarial samples used at the start of training may have limited use in helping the model be robust at the end. And after noticing this, we decided to propose this method called delayed adversarial training. And based on this observation that initial adversarial samples may not be that useful for final model robustness. So instead, we want to replace these initial adversarial samples with some other adversarial samples or some other kind of sample. And why not use natural training samples? These are free because we already have them. And we also anyway want our models to perform well and correctly classify natural training samples. And we actually can do a quick experiment to verify the merits of this method and if it's a promising direction. So the blue curves here show the performance, the test performance when regular adversarial training is used. So we have the natural accuracy on the left and the adversarial test accuracy on the right, where the testing and training adversary strengths are the same. We also then have these switching curves. And a switch is basically the epoch at which we switch from using natural training samples to adversarial training samples. And we can see that there's a very wide region where we can switch and still get comparable or in some cases actually better final test accuracy. We shouldn't switch too late. So by too late, I mean after the first learning rate drop, which is at epoch 100, because then the model will converge too much. But otherwise, we don't have to change any parameters or perform any other modifications to our training procedure. We just have to change the samples which we use. And it seems like we can get comparable performance. And yet we don't need to generate adversarial samples from the beginning when we are switching. Furthermore, we noticed that if you were to train the same model on natural samples, the training loss starts to stabilize around these epochs 55 to 85, which seems to suggest that the model is stabilizing then. And so we can actually come up with an automated switching criteria, which is detailed in our paper. And delayed adversarial training method doesn't require cross-validation or other methods to come up with a switching point. We can just do this at runtime because we would be using natural training samples until the time we do the switch. So if we look closer at these curves, we can actually see that the final accuracy when using delayed adversarial training is actually higher than regular adversarial training in many of the instances. And this has been observed in some other works where they didn't use natural training samples, but they used samples of weaker strength in the initial phase of training as well. And basically, when we use delayed adversarial training, our method is not making the model overfit to adversarial samples of little relevance in the initial phase of training. Instead, we're using natural training samples, which we would want to correctly classify. And we also, and we show this curve in our full paper, that the training loss using delayed adversarial training is higher than the regular training loss. And we're also getting higher accuracy, which indicates better generalization performance. So let's see how delayed adversarial training performs against regular adversarial training for a variety of different data sets and model architectures. So with CFAR10 and the wide ResNet, we can see that we get, we're getting over 60% time savings, and delayed adversarial training is giving us the highest accuracy. The adversarial accuracy, by the way, on this slide, the adversaries are at test time and training time are of the same strength over here. And for ResNet 18, we also get a very similar outcome, where we can get over 50% time savings and a higher adversarial test accuracy. For CFAR 100 and a small two-layer convolutional neural network for MNIST, we see similar performance and significant time savings again. We also decided to test our models, which are trained on using delayed adversarial training, against attacks of strengths which were not seen during training time. So in other words, we keep the epsilon ball size fixed, and we vary the number of projected gradient descent steps, or we keep the number of steps fixed, and we vary the size of the epsilon ball during test time. And we see that delayed adversarial training gives cause which almost similar or same profile as regular adversarial training, which shows that despite us using adversarial training samples much later on in delayed adversarial training, we are able to get similar generalization performance as regular adversarial training. And in fact, in some cases, as we've noticed, we get higher accuracy. This was with CFAR10 and the wide ResNet. With a ResNet 18 and CFAR10, we see the same phenomenon again. And this is with a two-layer CNN using MNIST. And MNIST has this very characteristic drop in accuracy that has been noted in other papers when the epsilon ball size is increased. And we can see that we're able to push this drop a little further. And during this period of steep descent, we can see that for an epsilon ball of this size, we can get extremely high differences in accuracy on the MNIST dataset. We also verify the black box attack performance. We generate test samples from independently trained copies of the network, copies that are trained using natural training, regular adversarial training, and delayed adversarial training. And consistent with the literature, the black box attacks deliver higher accuracy, and the naturally trained independent copy delivers the highest accuracy. So in summary, there's an initial phase of adversarial training where adversarial samples are of little relevance, and we can use delayed adversarial training by delaying when we start to use these adversarial training samples to get significant time savings and comparable accuracy, or in some cases actually even better accuracy due to better generalization. Please do check out our full paper for more details and more experimental results.